Okay, guys. So what we're going to do today is we're going to, this is sort of like a little tasting menu for chemistry. We're going to taste a little bit of this. We're going to taste a little bit of this. Some of the things that we're going to nibble on, guys, are going to be things we've done before. Some of these are going to be new. One of these things, and this is going to feel like heavy-handed almost, one of these things you're going to have to be able to do on the test and the AP test. And they demand, and it's weird, but they demand that you do it exactly the way we're about to talk about. You'll see. But guys, what we're doing now is we're talking about solution concentrations and tying that into the idea of dilution. You need to know how to do dilutions, how to create solutions for more concentrated solutions. Guys, honestly, I will not ask you to do these things in lab because honestly, it terrifies me. And I don't want you to have to do something that I don't like to do. But we'll talk. But you do need to know how to describe the process. And then we'll wrap up by talking quickly about titration, which is something that you did last year, but we'll touch on it briefly. So guys, with that said, remember our good friend molarity? Oh yeah. So guys, when we talk about solution concentrations, we are talking about the molarities of solutions. And these molarities, which we've just been talking about because we already understand them, are given in moles of solute per liter of solution. Define this clearly, but we have certainly dealt with it, but we need to address it clearly. Guys, when we talk about concentrations of solutions, we can actually express these in one of two ways. And guys, I would suggest to you this. Rather than writing down the bullet, you can certainly write down, can be expressed in two ways. But rather than write down the bullets, let's use them as a starting point to draw pictures. We understand, and you're going to be drawing pictures on Monday's test. Be ready for that. So guys, please don't write down the bullets. Let's draw pictures. So guys, what we're going to do is this. Let's draw a 1 molar solution of sodium chloride and a 1 molar solution of calcium chloride in a beaker. So let's make the one on the left the 1 molar sodium chloride, and let's make the one on the right the 1 molar calcium chloride. And guys, you should be able to draw what is in those beakers. But before we can start, let's specify, don't include the water. Now guys, understand at this point in the year on the test on Monday, we will not be including the water because we haven't talked specifically enough about the intermolecular forces that hold the water to the ions. But what you'll actually see on the AP test, if you're drawing salt solutions, they will have you include the water molecules and draw them oriented properly to the ions, but that's down the road. So we won't do that on the test. You guys good? All right, so let's draw. So, strong or weak electrolyte, or non-electrolyte, sodium chloride. Strong, weak, or none. You got to know this for the test. Strong, weak, or none. Strong electrolyte. All chlorides dissolved in water except for silver, lead, and mercury. So, guys, this is going to break into sodiums and chlorides, and that's what our solution looks like. When we're doing these representations, guys, we need the right ratios. So you could draw 1 of each, 2 of each, 3 of each, but if you drew 2 of one and 3 of the other, that's wrong because the ratios have got to be good. Good? Okay. Then guys, over here, we've got calcium and we've got chloride, and those are the substances that exist in that solution. Oh, you guys learned something a minute ago. Guys, no. Let's talk. So, Guys, if you kept those chlorines together like this, what is that? That's a gas. That's not in solution. That's up in the air killing people. So guys, that is not what we have in solution. And guys, listen carefully. If you're not sure why, hear this. Ready? There is no chlorine in calcium chloride. There is no chlorine in calcium. There is no chlorine in CaCl2. What is in CaCl2? Chloride ions. There are 2 of these, and neither one of those is chlorine. They couldn't be any more different than chlorine. Guys, that is not chlorine. That is chloride ion, and the only thing they share in common is 17 protons. This is completely not like chlorine. It's chloride. And that's what we have in solution. So guys, down here in solution, what we actually have is 1 minus, and another one of those 1 minus. And those aren't chlorine. Those are chloride, and that's different. You guys okay? Yeah. That's the next thing that we were going to talk about. So, guys, the idea is this. On our test, as I mentioned before, you just have to have the ratios right. 1 and 1, 1 and 2. But now let's talk about this. Because, guys, if we could assume that these are both 1 liters of solution. That's a weird sentence. Guys, what is the concentration of sodium ion? 1 molar. What's the concentration of chloride ion? Also 1 molar. Now guys, what about this? In this solution, what is the concentration of calcium ion? 1 molar. What is the concentration in total of chloride ion? 2 molar total, 1 molar of each. Now guys, understand that we didn't really need to define that we have a liter of each of these because those concentrations would hold true at any volume. But if we have a liter, we also have a mole and a mole and a mole and 2 moles. So this is the take-home message. Guys, this is 1 molar in sodium and it's 1 molar in chloride. Both of them is ions, sodium ion and chloride ion. This is then 2 molar in particles. Now let's go over here. What is the total molarity of the other solution in particles? 3 molar. So guys, in a very real way, the solution on the right is more concentrated than the solution on the left because this has got 3 molar concentration of ions. That's got 2 molar concentration of ions. So this would actually conduct electricity better. It would boil at a higher temperature. It would freeze at a lower temperature. This is literally more concentrated because there's more ions floating around in this one than in that one. Do you see the differences? Okay, so guys, what we're talking about there is not the concentration of the solute. What we're talking about there is the concentration of the particles. And you don't write this down, just you already see it. The concentration of the one on the left is 1 molar in each. The concentration of the one on the right was 1 molar in calcium, 2 molar in chloride, and 3 molar total. You okay? You get the ideas, right? Okay, so guys, with that said, we already know, don't write this down. Oh, did you need to go back?
Wait, doesn't 2 ways turn into 3 ways then?
What do you mean ways?
Oh wait, never mind.
You okay?
Molecules and particles.
There are molecules and particles. Go ahead.
How do you know that the chloride is 2 molar?
That we should talk about. So the way that we know is because we started with 1 molar CaCl2. And when that breaks apart, it breaks into 1 calcium and 2 chlorides, and we get 2 chlorides for every one of these, which means it'll be twice as concentrated. Is that okay? Are you sure?
So wait, why would it just be 1 if it's combined to be half
let's do this. Rather than talk about moles, let's talk about dozens. Okay? So imagine that you have a dozen of these molecules, and this molecule is actually the molecule PC2, which is pen 2 cap. Okay? So we've got this molecule called pen 2 cap. And if you have a dozen pen 2 caps, how many total pieces do you have? Well, if you break this apart, each of these is going to break into 3 things. So if you have one of these, you've got 3 pieces. What if you have a dozen of them? So if you have a dozen pen 2 caps, then how many total pieces do you have? 3 dozen, right? The same logic is true here. If you have 1 molar of this and you break it apart, you're going to end up with 3 molar particles because this breaks into 3 bits. You get the idea? Is that okay? I just made that up on the fly. That wasn't bad. I know, right? There you go. I should be a teacher. Okay, so you guys good? All right, so now guys, you know this. We can use molarity. We need to talk about solution prep. Write this down word for stinking word. Sort of. Actually, no. Write the equation down word for word. And here's the way this goes. So, guys, for those of you that are in second period, you just got done doing a lab. And in the lab, you were messing around with sulfuric and hydrochloric acid. Were they both 1 molar solutions? Okay. The question is this: where does that stuff come from? This stuff is death in a bottle. This is actually saturated sulfuric acid. It is impossible to make sulfuric acid any more concentrated than this at room temperature. This is 18 molar sulfuric acid. You get this on you, you've got a matter of moments, and I've done that. It's pain like you've never experienced in your life. It's wacky. Guys, 9 years ago when we moved into the new building, most of you were still in diapers. Sorry. But guys, 9 years ago when we moved into this building, and maybe some of you remember this because you live in the local wards, it was amazing. Frankly, it almost brought tears to my eyes. Did any of you see the moving process? I'm going to take these off. I'm a little distant from that. Guys, we did it in a day. We moved all of Orem High School out of the old building, which is where the soccer fields are now, and into our new building in a day. It was unbelievable. All of the members of the local wards came, and guys, literally, we made a bucket brigade, and it looked like ants marching across the field. And these people, I mean, from 5-year-olds to 95-year-olds would just walk into every classroom. They broke up into teams and they said, "Mr. Nabberger, this is your team." I didn't know any of them. And they just came in and they grabbed my stuff and they carried it into my room. And it just happened in a day. It was unbelievable. And there was this older gentleman, lovely man, probably in his late 70s, early 80s. And he had been a chemistry professor over at BYU. So they sent him to me and they said, "Because you know chemistry," because I didn't have to just move my classroom, I had to move the lab. And there were just people everywhere, and eventually I was incapable of monitoring what was going on. And this older gentleman, he was fairly feeble, decided that he was going to just go into my lab and start moving chemicals without me knowing it. And he's walking over to the new building with this plastic thing with 2 bottles of concentrated sulfuric acid. And you can see when you go into lab next time, you'll see the damage still. Can you picture my counter at the front of my old, next door, the front of the room over there, and there's a counter there. And he went to sit this down, and he didn't get it all the way on the countertop. And when he let go, it teetered and fell. And one of these bottles hit the floor and bounced. The other one hit the floor and it shattered. and it got on him, and it was, I mean, we had to bathe him in baking soda. The person down. I mean, I'm running across. Anyway, so I get in there, and he's got sulfuric acid on him, and we bathed him in baking soda, and we took care of him. And guys, it ate a hole in the floor. Like, they were done with the building, and they actually had to bring the tile guys back and rip up the floor and retile. If you look in front of my counter, you can see the tiles are a little different colored because they couldn't find an exact match. And they had to replace the paneling on the front of my counter, and you'll see that it looks different. It was just, I hate this stuff. So the question then becomes this: if this stuff is so nasty, why on earth do I buy it? I have to. Guys, this is the only way that I can get sulfuric acid. So guys, the question is why? Why would they send me this Satan juice? Why do they sell this stuff? And that's it. It's so that we can make way more of this stuff. Because guys, it doesn't matter if this stuff is 18 molar or 0.18 molar. It's dangerous to ship, and it's very expensive to ship. So long as they're shipping it, they may as well sell it to you really concentrated, and then you can dilute it. So guys, I'm in my 26th year of teaching, and I've only had to order more sulfuric acid twice. That's it. I go through a bottle about every 8 to 10 years. Let me explain to you why. So guys, in order to figure this out, you've got to understand the idea of dilution. And guys, include this in your notes. So guys, we don't buy sulfuric acid or hydrochloric acid or nitric acid or acetic acid. We don't buy this stuff at the concentrations we use it. We buy it concentrated. Don't write this down. But the idea is this. Routinely what we do in lab is we buy the concentrates and then we water them down. In order to do this, we need what is called a dilution ratio. Stop. Now write this down. Guys, this is the equation you need to know. It is not on the AP equation sheet. They assume that this is fundamental enough that you can just use it. And it says this: molarity initial times volume initial is equal to molarity final times volume final. So guys, in order to manipulate this equation, we need a scenario. So, did we use 0.1 molar sulfuric acid in the lab, or was it 1 molar? Doesn't matter. It's still pretty scary stuff at 0.1 molar. So guys, don't write it down, but let's read this together. So it says this: stock sulfuric acid is 18 molar, and it is. There's the bottle. So the question is, how could you use this solution to create a quarter liter, 25 milliliter, 250 milliliter? It's about a pop can. Really close. So how would you use this to make 250 milliliters of 0.1 molar sulfuric acid, which is more like what we would use in lab? Here's the answer. Do this with me. So guys, we're going to go molarity initial times volume initial is equal to molarity final times volume final. Now we're going to plug in the data that we know and solve for what we don't. So guys, what is the initial molarity of the acid? 18 molar. Nitric is about 16 molar. Hydrochloric is about 12. But this is 18 molar. Now guys, this is our X. What we're trying to figure out is how much of this horrible stuff do we need? Well, need to do what? Well, we are going to make a solution that is finally 0.100 molar, and we want 250 milliliters of this stuff. Did I screw up? Am I okay? Okay. So guys, let's solve this. So we go 0.1 times 250 divided by 18. 3 significant digits. We'll assume that the 250 is perfect. 1.2 You starting to get it? So guys, how much of this stuff do we need? Well, if you don't remember, this is a milliliter. We need 1.39 milliliters of the horrible stuff, and we can make enough 0.1 molar sulfuric acid to basically run an entire lab for all of you for the day. So we literally use this stuff milliliters at a time. I shouldn't do this, but this is 2.5 liters. So this is 2,500 milliliters, and we use it milliliters at a time. You understand why that lasts so long? Okay. But guys, here's the problem. We haven't answered the question. What does the question say? How do you make the solution? So guys, we need to answer the question. You need to write this down because this is what you're going to be responsible for on the test. So guys, they're going to hold your hand to the fire on this one. Remember that number. We're going to do this together. Now we're going to answer the question, how do we make the solution? Step number 1 is this. Put on goggles, gloves, and an apron. If you don't write that down, you won't get credit for this on the AP test. This is the AP author's efforts at stressing lab safety. I'm serious. You actually have to write down, put on goggles, gloves, and an apron. Yeah.
So is the relationship between like what we were doing earlier, like polarity, is that like exponential? Like,
It's linear. It's linear. Okay. Now, guys, here's the trick. We've already done the math, right? It was at 1.39 milliliters. Okay. This, let me show you, and then we'll turn this into a procedure. Guys, so eventually what we're going to do is we are going to make 250 milliliters of a solution. Let me introduce you to somebody. Guys, this is what is called a volumetric flask. That is a word, and we'll write it down in a minute, but that is a word that you need to know. We will be using these in lab. These are stupid expensive. So guys, let's talk about this. If we needed 250 milliliters of water, why won't this do? It's not accurate. So guys, what have we been talking about? How do we make labware accurate? Calibrate it. This comes to you pre-calibrated. That's why it's so expensive. So when they make these, what they actually do is they cast the glass, and every single one of these is actually hand calibrated. It's actually done by a machine, but it's as if it was hand calibrated. And here's what they do. Remember how we did in lab densities, mass divided by volume? We figured out the volume of a mass of water based upon the density given temperature. How was that? What they do is this. They measure out exactly 250 milliliters of water. And they don't measure its volume, they do it by mass, and they can get out to 6 decimal places. Then what they do is they place that water into every single, what are they called? Volumetric flasks. And then, guys, they etch this with a laser. You probably can't see it, but there's only one line on this entire thing other than right here it says 250. Guys, they etch it with a laser, and the only thing that this thing can do is measure 250 milliliters, and it's exactly there. That's why this neck is so narrow and tall. Some of them the lines up here, some of them the lines down there, but they know within the tolerances of their ability to make the bulb that 250 is going to be somewhere in here, and they laser etch exactly where 250 is. That's what makes these so expensive, is they come to us pre-calibrated. They're like 40 bucks each, so they're a little pricey. So this then is what we're going to do. This is how we're going to make our solution. Step number 2 is this. Partially fill a 250 milliliter volumetric flask with distilled water. You don't mention distilled water, it's wrong. Again, they're not my rules, but that's the deal. Oh, you can say either one. It's got to be distilled. We're a chemistry class. We can use either. Then, guys, number 3. Carefully add 1.39 milliliters concentrated H2SO4. That's why we did the math. I don't think they'd mark it wrong if you didn't, but step 4, no, sorry, not that. Step 4, swirl to mix. Do not put a stirring rod in there. Then, step 5, fill with additional distilled water to 250 milliliter line. That's what they're looking for, gang. In theory, no. It wouldn't be wrong if you put it, but you're okay if you don't. Let's do questions. There's one other thing we need to talk about, but go ahead. Sort of. There is one lab that we're going to do where you will actually make not your own acid, but your own base. And to do that, I will provide you with a solution of 20 molar sodium hydroxide. It actually takes me a couple days to make because sodium hydroxide, so all of the strong, let's say this, all of the strong bases are salts, right? They're hydroxide salts of the group 1 and heavy group 2 metals. And so I have all the strong bases in bottles, but they're in pellet form. And so what I have to do to give you the stock solution is actually dissolve an unbelievable amount of pellets in an unbelievably small amount of water. And so it takes a couple days to make. So I make about 250 milliliters of it, and you have to put it on a stirring plate, so it's always stirring, that also has a heater under it that warms it up, and you add it like 10 grams at a time over the course of a couple days. It's horrible. So yeah, you will do that one, yeah. Yeah, good question, and the answer is with a graduated pipette. Remember how we have the little droppers we can even do better than that. We have droppers that are actually graduated down to tenths of milliliters, and then we estimate to hundredths. So we can do it, yeah. Yeah, but sulfuric acid, I mean, all of the strong acids we can house in glass. The strong acids are by far not the hardest to contain acids. There are acids that you can actually only contain in wax. Yeah, because they'll eat through everything else. Hydrofluoric acid is an example, but there are other acids. It's actually interesting. The guy, it's not the guy from Vsauce. It's the guy from, it is SciShow. Yeah, he actually just did a video on the 10 most corrosive substances on Earth, and it crazy. Yeah, I don't remember, but just look it up. Guys, there is one thing we do need to talk about, however. You gotta, if you understand the theory, you won't make the mistake. But guys, please hear this. When we do this process, if you can picture what we're doing, guys, what we're going to do is we are going to put water in the flask, and then we're going to add acid. Notice what we didn't do. We didn't put acid in the flask and then add water. Let's talk about why. So guys, the rule is this. You always add acid to water. You never add water to acid. Do you want to jot down just a note on that? Let's do this. Always acid into water. You always add acid to water. Never do it backwards. You're going to get hurt. Now, guys, let's talk about why. So, and this is obviously not distilled water, but the idea is this. When you mix acid in water, it is a very violent exothermic reaction. So much so that if you were to carry out this process, you actually wouldn't be able to hold on to the vessel. It would get so warm. It's very, very exothermic. And actually, if it happens quickly enough, the solution will boil. And if it boils, it's going to go everywhere. Okay, so imagine this. If this is water, and I know 1.39 milliliters, not much, right? But what if you needed more? If you were dumping the acid into water and this boiled, what is mostly going to be coming out of the schnozzle is going to be water. Because as you dump this in, it's mostly water. You've added a little bit of acid, and if it goes, most of what's coming out will be water. In addition, there's a lot of water in here to soak up the heat that's being released as the acid reacts. Now imagine if this was full of acid and you dumped in water and that went. Most of what's coming out will be acid. So guys, you always start with a lot of water and then add acid to it. So you always add acid to water, never water to acid. Yeah?
Is that why you're concentrating when you concentrate that one thing for 2 days? Is that why you do
No, the reason you do that a little bit of a time is if you think, if you can picture what happens when things dissolve, water molecules surround the stuff that's dissolving. And if you don't do it slowly, you can't get the water to organize around all of the hydroxide groups that's necessary to make a 20 molar solution, and it just stops dissolving. So the reason you do that progressively is it gives the water time to get organized and dissolve more stuff than it wants to. Go ahead.
So when you're adding the uric acid,
Mhm.
add it slowly, so like that.
And that's the point. You want to add it, because if you were to just dump it in there, the surface of it could flash boil and it could go, which is why I chose to add the word carefully. Yeah. You guys good? Okay. So guys, this would be something to study for the test. Levi, did that start to sound like a study guide?
A little bit.
Okay. Just checking. All right, so guys, finally then titration. So if you hear the word titration and you're thinking to yourself, not quite sure what that's all about, let me remind you quickly. So guys, remember this back in May? Yeah, so guys, we went into lab and we went over here to the titration bench. here and we grabbed some HCl and we grabbed some NaOH and we went back out here and we brought these into lab and we took the NaOH and we stuck it in here. Remember? And then we reached in here and we grabbed a beaker and we went like this and we took the HCl and we stuck it in here and we stuck it in here and we stuck it on here and we gave it a stir and we added some phenolphthalein and then we dumped this in here and off it went, and then all of a sudden this thing magically turned pink, and we gathered some data, and when we were all done with that, it allowed us to calculate the concentration of this acid, which we pretended we didn't know, and then we came back and we said, oh my gosh, we actually do know it, and we figured out that our data was amazingly good because titration works amazingly well. Well, guys, in lab, we are going to actually do 7 different titrations starting in late February. For now, what you need to understand is that this process, so the process of titration is simply the process of adding two solutions together in an organized way. Guys, when we do this, you're going to see that you're going to be doing some problem solving. And there are some common threads. These aren't steps, because you know there's no such thing as steps in AP chemistry. But guys, there are some things that you may want to think about as you're solving these problems. And you may be saying to yourself right now, wait a minute, last year we had steps. Step number 1 was write a balanced equation. Step number 2 was solve for moles of standard. Step number 3 was the mole to mole ratio. And step number 4 was calculate the concentration of the unknown. Yeah, there were steps last year, but guys, last year you only ran into problems where you were figuring out the concentration of the unknown. That's not the case anymore. So, things that you may want to think about. Balanced equations first. Always balanced equations. Guys, balanced equations in this class become your security blanket. Because when you don't know what to do, write a balanced equation. Now at least you're doing something. And that process of doing something many times will lead you to the next something. So guys, balanced equations. Thought number 2, most of the time these end up being dimensional analysis problems. Pick a starting point and a goal. That will generally involve a stoichiometric ratio, which can be conveniently found in the balanced equation. And then guys, sometimes you're going to end up needing to do external calculations, like calculating molarity. All right. But guys, with that said, what I'd like to do is play with one of these with you. Shall we? So you decide for some warped and unexplainable reason that you want to become a research chemist. And you finish up your degree and you end up getting a job in an analytic lab. And somebody brings you a sample of a solution and they say, hey, we know that this contains chloride ion, but we need to know how much chloride is in this sample. There are permissible levels above which we can't use this water to irrigate our crops. We need to know. So what are we going to do? Well, guys, they bring you a solution, and the question they want answered is how many grams of chloride ion is in this water? Well, we're going to find out for them and make a lot of money. So, guys, first of all, let's do this. As we read the problem, the question says, how many grams of chloride ion are in a sample of water if 20.2 milliliters of 0.1 molar silver ion is required to react with all the chloride? Well, guys, based upon that, and some of you right now, the wheels are churning, Based upon that, we have enough information in order to answer the question. But to do so, guys, I would propose that it might be helpful to draw ourselves a picture, shall we? That's obviously a titration apparatus. Or it could be a missile ready for launch. It could be hieroglyphics. This is actually the Egyptian fertility symbol. Okay, maybe it's not, but okay. So guys, the idea is this. You are now going to, for your client, carry out a titration. So down here in your beaker, you're going to put your unknown. The thing that you know about this unknown is that it contains chloride ion. The question you're trying to answer is, how many grams? So, we need something up here in our burette that we can use to titrate our chloride ion so that we can figure out how much chloride ion is in there. You'll notice that it tells you in the problem what that something is. What's our something? Oh, silver ion. But guys, there's no such thing as silver ion solution. You can't make silver ion solution. If you have a piece of silver jewelry and huck it in water, it will never dissolve. So guys, where do we get silver ion solution? What could we use to make silver ion solution? Silver nitrate. Sorry, I heard it before I heard you, Jessica. Guys, what we actually are going to use is silver nitrate. The presence of the nitrate makes a salt which then dissolves in water, and now we have silver ion solution. So guys, why didn't they mention the nitrate? Why didn't they mention the nitrate? Which we don't call a bystander, it is a spectator. There's no reason to include the spectator because it's not doing chemistry, but when we go in the lab to do this actual process, you can't grab a bottle of silver ion solution. You can grab a bottle of silver nitrate solution, and that's what you're actually working with. So, guys, imagine this. Imagine that we then add, drop by drop, silver nitrate solution to this unknown solution of chloride ion. Guys, what are we going to see down in the beaker? A precipitate form. What will that precipitate be? Silver chloride. What will it look like? What color is it? You just made some in lab, guys. You'd better know this. What color is silver chloride? It is white. So guys, picture it with me. Join me. Picture it with me. Every time a drop of silver nitrate hits the solution, you're going to see white and white and white. And how do you know when all the chloride's tied up in silver chloride? When you add a drop and there's no more white. And guys, that's what this titration will look like. You will add the silver nitrate solution drop by drop until that one drop does not form any precipitate. Why does that no longer form precipitate? Because all of the chloride is tied up and none of it's now available to make more precipitate. When did that happen? That happened when we added 20.2 milliliters of silver ion solution. And guys, that is all the information that we need in order to figure out how many grams of chloride is in the solution. So how do we do it? Well, guys, the first thing we need is a balanced equation. But guys, all we're doing is this. We're making silver chloride. That's our net ionic equation. The silver from our silver nitrate is tying up the chloride in our test sample. We're making silver chloride. So guys, oh, this is going to work out great. Watch this. So guys, now let's set up a problem. What are we solving for? What do we want to know? Grams of chloride. So we're going to go over here and we're going to go grams of chloride. I promise this wasn't planned. Now guys, What do we know about the process that we engaged in that will help us figure out how many grams of chloride? We used 20.2 milliliters of our silver ion solution. The more we used, the more chloride must have been there. I again promise this wasn't. What started as a label became the starting point for our dimensional analysis. Now, guys, we've got to figure out how to get from milliliters to grams of chloride. So, 1,000 milliliters is 1 liter. Why would I want to be in liters? Because once I'm in liters, what can I go to? Moles. How do I get there? The molarity. Because every 1 liter of this solution contains 0.001 moles of silver. Is that right? Yep. Oh, sorry. You don't listen, just watch. Now, guys, we're in moles of silver. But we want to be in moles of chlorine. Chloride. How do we get there? Mole stoichiometry. Balanced equation. 1 mole of silver ion will react with 1 mole of chloride ion. Forgive me, guys, I'm running out of space. Now, can we get to grams? Sure. 1 mole of chloride ion has a mass of 35.5 grams right off the periodic table. And we've got 20.2 divided by 1,000 times 0.1 times 35.5, and 3 significant digits, 0.0717 grams of chloride ion. Okay. So guys, here's the scoop. This is your homework. Now, guys, Monday's going to be different. When I see you on Monday, we are not going to review the homework. Never review homework on a test day. You will come in, and I will give you all credit for the homework because I'm going to assume it's done. And when that bell rings, guys, we're starting the test. The test is timed. We'll talk about the timing a little bit, but when the bell rings, 3rd period, we are starting the test. So if you have questions about the homework, you need to address it outside of class time. And guys, when the bell rings, we're starting the test. So bring calculators, bring pencils, bring all of that happy stuff. And again, if you have homework questions, get them asked and answered outside of class. Yeah. Yeah, so the periodic table that you will get on the test will be the one that you get from the AP people, which apparently I can't find. The usual, But you will not be using the periodic table that you brought in from last year. Yeah. Uh-huh.